This
session. So
conference
at the
will
end of
now
the
be recorded.
So once again, welcome to Mirrorless Design's webinar on mapping autonomous driving algorithms onto distributed multi-core ECUs. I'm your host, Deepak Shankar, and in the next 45 minutes, I will be walking you through a variety of models and a variety of design structures that will give you a very good understanding of how you can map your algorithms onto a highly distributed architecture someday that may not even be available to you at the start of your project. I'm going to start off with some of the challenges in designing the system, going to the concept of hardware-software partitioning, showing you some examples, and finally wrapping up with functional safety. Everything today in the automotive driving world relates to SOTIF and to ASIL and to ISO 26262. So we're going to concentrate and talk about some of those aspects as well. Let's start with the introduction challenges in designing autonomous driving systems. The goals are to provide a platform where architects and system designers of autonomous driving systems can really collaborate and experiment. There's a lot of technology, there's a lot of capabilities, a lot of features that are in autonomous driving, and being able to combine all of that into one application and then making sure it's all running fine is a pretty considerable and a pretty hard job. So being able to do it upfront, very early in the design process, will allow you to eliminate a lot of the bugs and bottlenecks before you start delivering the product or before you start even development of the software or the system. Now, some of the things that are very critical in autonomous driving is experimenting with different scheduling techniques, especially when you're going to multi-core architectures and where these multi-core architectures are across diverse ECUs on a highly distributed Ethernet or CAN plus Ethernet with gateway network. Now, the goal of this platform is to really explore, test, and analyze. So you want to try out different mapping techniques by not just providing all of the software on a single ECU, but distributing it across the vehicle. So that way you can minimize your risk, and also testing it for various failure conditions and also for different sizes or configurations of the ECU or the network. The last use of this platform is to really try out different use cases in vehicle design. So every vehicle is going to have a different location for their cameras, for their radars, for their LiDARs, for the sensors, and all the different pieces of information that is required by autonomous driving. So to be able to truly evaluate your autonomous driving system, you need to first understand what is going to be the location of the ECUs relative to the network. And this is a critical element in making a decision on how you distribute your application. Now, when we look at the autonomous driving, first and foremost is experimenting with mapping functions, which is really that, say you have a single ECU with a single processor with a multi-core, how do you meet power and timing requirements? I'm going to move over to Visual Sim and start off with a very, very simple description of a system. So what you're looking at here is you have 4 completely independent threads, and they're all running at different rates, so they're triggered or at a different periodic events, and they all have different processing time schedules. Now, initially, I'm going to start off with something that has 4 cores, which is right over here, and I'm not going to have any shifts, which means they're all going to be on their own independent periodic processing element. What I'm looking for here is trying to understand what would be the response time when I have a single core versus 4 core, and what will be the associated power consumption. So I'm going to run these 4 threads on my multi-core, and you will see that I get a variety of statistics. And let me focus first on the assignment of the tasks. And I'm going to go into a sub-region over here and zoom into it. So you can see each one of these tasks take a variable amount of time. You can see this is 1 and 2 and 3 and 4. And then they all get mapped to different ECUs. The color indicates which ECU they're getting mapped to. Similarly, here, I can see what the response times are over the period of the simulation. So, but here we're looking at, this is your 1, 2, 3, 4, and then that's your in-between one, and then again 1, 2, 3, 4. So what this does is it shows you what is going to be the response time for each one of these different tasks. Now, the other aspect is that, anytime you do a design, performance is not the only attribute. You want to also look at the power consumption. So here the red line shows me the average and the blue line shows me my instantaneous. What that means is it's telling me over time when each element got activated or moved over to standby or sometimes even into idle or other states. So using this, for example, I can change different attributes, and I'm going to talk about the attributes later on, but just, I'm going to have a shift here, and I'm going to go ahead and rerun it. And one of the things you're going to notice is instantly the power consumption changed. I just made one thing, which is I made sure they were not all overlapping at the same point, but rather they got shifted out a little bit. And immediately you saw almost a 3.5x drop in power consumption and also a much lower average power. Now, the reason being is when I zoom in here, you will notice that most of the time there's only one core used, and there's only some occasional periods of time where you can see a second core being applied. So by doing certain reorganization of your software, you can actually get significantly better performance and still keep it at a much cheaper, lower cost, lesser number of core architectures, and also reduce your thermal impact. Now, another aspect, and this is the critical part. So we saw the basic concept of mapping of functions to multi-core. Now let's take it to something more specific. Here what we have is we have the logical, which is, you have the engine and braking function sending data to each other. You have the EPS body, and then you have the autonomous driving functions. You have 1, 2, and 3, and each one is getting mapped to different ECUs. So here's the process where we're taking these functions, all of these different functions, and mapping them to different ECUs. So, for example, of course, the engine, brake, EPS body, they get mapped to their regular ones. But then the autonomous driving, for example, this one here is getting mapped to the ECU. Function 2 is getting mapped to engine, and function 3 has got multiple things, so it's getting mapped to EPS, ADAS ECU, and to other ECUs. So there is also this aspect of where there's also a distributed network across them. So now your challenge here is, how do you take something that is completely logical, which shows all the connectivity and communication between all the functions, and then map them to a real network? So now moving over to Visual Sim, so we can look at what this network would look like. I'm going to open up the model. So what you see over here is my network, which is I've got the 6 functions hanging off any CAN network. Now each one of these is corresponding to the regular operations that we saw in the vehicle, which was these functions are listed there. And then of course the different ADAS functions is 1, 2, and 3, and you can see the dependency. So 1 click triggers 2, but 3 needs 1 and 2 to finish before it can actually compete. So what you have now is an ECU network, and you have an autonomous driving function, and each one gets mapped to different networks. Now also each one of these requires a different set of sensor data that must be available before it can fire. So it needs the data, plus it needs to be fired on one of these cores. So not only is your configuration depend on putting it on different ECUs, but also you have to consider there's existing function of the ECU, and also when you have movement of data, you're going to have transfers, which is like function 1 is executing on EPS ECU. Function 2, which depends on function 1, gets executed on brake ECU. So guess what? And on engine ECU, which means EPS1 will have to send data across the network to engine 2 and also across the gateway, across this to brake ECU as well. So you have a lot of challenges that would apply in your particular system in terms of trying to do this partitioning. Now, another aspect, and this is really the goal of your distribution and of the mapping, is what is the timing deadline. So for example, here, I was expecting task 3 to complete at this time, but in reality, it completes over here, which causes other performance problems because it's not like, for example, a braking system does not brake in time, or for example, the turn does not take place within the within the white line, things like that. So now, what happened in this particular case? As you'll notice, T3 started off, but then it was preempted by T1 and T2 until it got a chance over here to go ahead and complete the task. So you can start looking at impact of priority, you can start looking at impact availability of resources, availability of data in the form of sensor values stored in a variable or register. So you can look at all of these attributes to see if you meet your timing deadlines. Now, a bigger problem, and we saw a little bit of that over here on the logical to physical, is really the impact of network configuration. Because now, not only are you worried about communicating within the vehicle, but you also communicate outside of the vehicle. You go to 4G, 5G, Bluetooth, DSRC to the toll gates, all of those things. Plus, you have to go across gateways to get to the eventual system. So when you do that, your latency increases, and at the same time, how you allocate your tasks become very critical. Do you do it closer to, say, for example, into your radar subsystem, or do you do it closer to where the decision is being made? So a lot of the partitioning of the different tasks within the function becomes critical. Of course, one of the other things is you're looking at the hardware-software requirements, which can change by package. If I have a rural package versus urban package versus combo rural and urban versus level 3 versus level 1. So there's so many combinations. And of course, if I'm doing a Toyota versus an Audi versus a GM car, the locations of the sensors, locations of the LiDARs and radar systems would be completely different. So they'd be across a multitude of networks. So now what you have to do is you have to look at how do I allocate these tasks across this network system. And finally, the last thing is once I've designed something that looks like this, I need to generate documentation that allows me to then share these with the rest of the customers or with my partners, either an OEM or tier 1 or semiconductor companies. So you take a system like this, which we're focusing on the braking, and I'm going to go ahead and export this to the web. I'm going to say, go ahead and export it. I'm going to give it a nice background color. I'm going to say, go ahead and generate all the files. We're going to do it in PNG. Go ahead and run it. And in a matter of about 10 to 15 seconds, we're actually going to get a complete specification available to you for for the entire system that you've constructed. So it's not just the data. It's not just the block diagram or anything like that, but everything that you have stored or represented in your model would be captured as part of this output that you get. And as we run the simulation, I'm going to talk about these simulation models a little later with the analysis. So I'm not going to talk about the outputs here right now, just to show that it's, the documents are being generated. Now, in the meantime, if anybody has any questions, go ahead and ask the questions so we can answer them as and when the questions will be asked. Okay, there we go. So now what's happened is you got the complete documentation with all the details. I can click on these and I can look at what was inside of this. I can look at the specification of my CAN nodes. I can look at the specification of my gateways. I can also look at what's the settings for different configuration tables. I can provide that look at that information as well. Plus, what I can do is I can go into different components. Like, for example, I can go in here, I can click on this, and I can view what the power consumption was. Similarly, I can go back in here. I can look at the wheels. Just the plotting is not there. Look at the stats over here. I can look at the braking mechanism, and I can look at what the latency was. So not only am I getting the spec, but I'm also getting all of this additional information that is now available to me as part of this particular model that I constructed. So it can all be exported out. Now moving on to the rest of the system. Now let's learn a little bit about the hardware-software partitioning concepts or the problems. The main thing is you need to construct a network model. So there's your CANs, LINs, Ethernet, ECU. You want to construct the network. Then you want to associate the ECUs and sensors to each of the nodes. And then you want to define the software tasks, including the messages, the periodic triggers, the events. You want to define all of those against each of the ECUs. And then finally, you want to measure the response time and network utilization. If I look at this one here is where I've got 8 ECUs, and each one has sensors and different ECUs, different nodes connected to them. I'm sorry. I've got 8 ECUs, and each of them is connected to a separate node on the network, and each of them has a local sensor. Now, there is the aspect of the behavior, which is what is my application doing. So here, for example, you can see ECU1, there's a message that's triggered, looks at emission, watchdog, and reception. If I look at ECU4, you can say the image capture, decode, manipulation, graphics overlay, and display drive. So now, some of these have dependencies where some of these functions are triggering other functions, while in some cases they may be triggered on a schedule. So this one, for example, ECU1, when it's done, triggers ECU2. Now, in addition to that, ECU2 also requires local sensors. So if you look at this, you can see this one triggers this, that's a control, but I also need my local sensor data before this flow can be fired. Here, for example, I need my sensor plus I need an accelerometer. So different parts of the system would require different activities in my design different sensors and different triggers or interrupts from other applications. Now, what I can do here is, going back, is I can move some of the sensors from one ECU to another one. I can move the software tasks to be not running on ECU1, move them to ECU2. I can try all of those combinations. That forms the hardware-software partitioning aspect of your design. Now, in this particular case, you have independent processors, but as I showed you right up front, You can even have multi-core within each of the processors. Now, let's take for a second and look at what is a requirement. So what are all the library components that are required to very quickly assemble up such a system? Now, when I look at this, this is the system level block libraries, and this is what we have in Visual Sim, and you can see there's a variety of components. So for example, you can have CAN, time-triggered Ethernet, FlexRay, TSN. You can also have things such as within your system PCI Express, or an ARM-based architecture, or an FPGA, or even different types of operating systems. So the tool must provide you all of these different capabilities to very quickly assemble an autonomous driving system. Now, let's look at definition of the system and the associated application on top of it. One of the key things about any of these systems is to remember that you want to consider power, timing, throughput, and also the application of functionality. So, for example, when you start off by constructing a model with just the timing, then you add other aspects like scheduling, arbitration, any AI algorithms, things like that. And then you update the power table with a list of states and the associated power and any power management. So that's your state diagram. So you associate that. So now what you've done is you've taken the timing, you've taken the functionality, you've taken the power. Now you can essentially run simulations where you can study power consumption versus throughput. Or for example, I can look at, packet data sizes versus latency. Any combination of analysis to come up with what's my best configuration. Remember, all analyses are really based on system activity and state changes that will impact your power, performance, and time for functionality. Now, if you take Visual Sim, the way we start off is typically you have some sort of a trace file, say an ARXML or some other network trace like wires. And then you can also bring in spreadsheets of analytical models that you might have constructed. These models are then, or this data is then fed into a simulation model where it runs the simulation and then you can see the generated reports. For example, over here, the power information was taken from the table here. And if you notice, the average case was right down here. But the real case, which is based on your application or your use case, is a completely different power model. So using the model, you can actually run simulations and try out different experiments to come up with the right configuration. Now, before we get further along looking at demos in detail, let's talk a little bit about the structure of a model. You have the libraries here. You drag and drop components from the libraries, and then you assemble up a model. You have the platform, and the platform has the details of all your hardware, any operating system, things like that. And then, of course, you have your workloads, which are your traffic, your interrupts, your periodic updates, sensors, any of those kind of things that trigger your applications, either directly or indirectly. And the applications themselves can be described as a sequence of, with connections and, dependencies and feedback loops. You can have all of those applications, and you can have multiple applications running concurrently in your system. Of course, one of the key aspects of these applications is you can also have the impact of priority in the design. Now, this is the model itself. So this is where you're running the model against a particular platform or running a model of the application against the platform. Now, you can try out different parameters. So this is where I can change the mapping for these flows from, say, I don't want to go all CPU1, I want to go partly to CPU2, which means my transfer time will also be impacted because now if I have to go to DCPU, I can just go across this bus. If I got to go from CPU 1 to this, I'd have to go right across this. But to get to CPU 2 from IO 1, I have overhead right there. So there's a lot of trade-offs between your task activity, which is the processing time, and the transfer, which is data going across the network. The other aspect is adding power-related information, and also your reports or your statistics are also output here. Now, let's look at an example of hardware-software partitioning of the autonomous driving system. Now, we'll go back to that same block diagram we saw earlier, and you can see how the different tasks are being assigned in this particular design, which is, I have my regular tasks, and then I have my autonomous driving tasks. Now, when I take a model, I have to look at the power, I have to look at the network, I have to do my regular scheduled task, which is here, it's being mapped to each one of these. So engine is mapped here, EPS is mapped over here. So they all get mapped onto these different ECUs. The reason they're separated out is because then it's easier for us to be able to visualize it, make changes to like the functions or to the ECUs or to the hardware or the network platform. I don't have to change the other items. So that's one of the reasons why they're all separated out. Then, of course, there's all the sensor data. If you remember, all of them have dependencies on sensors. Sensor data that gets fed into each of these ECUs across the network. Lastly, you have the definition of the autonomous driving. And you want to put in, what's the best configuration of mapping each function to one of the ECUs. Now, this is my model. So I got the different functions. I've got the autonomous driving at the bottom. I've got my list of I've got my list of sensors with all the data values and in the rates and the start times, has all that information. And of course, I have my different ECUs with their values of the bus, the clock rate, the number of cores, the mem speed. All of those attributes are listed right over here for each one of the units. So now I'm going to go ahead and run this. Now remember here, it's always a power performance trade-off. So we're always interested in both of the aspects. So for example, here, we're looking at the power consumption. Now here, one thing that's interesting is you can see it has these occasional peak loading. Doesn't happen very often, but it happens about every 10 milliseconds. So it is fairly substantial if we take the life of the car, because this can overload and it can cause battery damage or maybe even reduce the life cycle of the battery. Now, when I zoom into something here, you can actually see that most of the functions are happening below 1.7 watts of power right over here. Now, when I look at some of these functions right over here, you can see the autonomous driving functions are, their latencies are listed here. Okay, so you can see here my autonomous driving function 1, function 2, and here we go. This is the latency associated with the entire autonomous driving. So you can see what my total autonomous driving latency was relative to the rest of the functions. So here you can see all the other functions, body, engine, EPS, braking, everything else. Plus, you can also see what is the throughput I'm getting across each one of these memories. I can look at the, what was the max latency for different components. I can see all of those information as well, in addition to the power consumption. Now, what I can do is, for example, I can see what my transfer node is. I can see what my autonomous driving, I can see number of transfers. It gives me all the information I need. I can put it right here into the document. So it kind of, speeds up my whole development as well, because now I can actually, run simulations and try out things, try out these different conditions or different cases before I go off and build the product. Now, one of the challenges that comes up is very early in the design process, you don't really know all the details. You have very little details about what exactly the your system is going to do, and you have a lot of multiple independent processing computers or ECUs, and you need to start distribute the software. But you don't have details about all the other functions. You don't have details about exactly what the network configuration is, all of those things. But you need to provide early data. So like what should be my routing table? What should be the planned capacity at the ECU and of the network? How do I allocate these threads? So I have to look at those right up front with very little information. So here's a case where I've got 4 tasks and they're connected. So T1, T2 and ECU1, T3 is on 2 and T4 is on 3. You can see the messages I've got between them. I've got M1 to M4. And this is the network configuration. I got 2 ECUs on one CAN connected through bridges, and then I go off to CAN 3, which has the 3rd ECU. Now, the way messages are set up is that they're internal to an ECU. That means the source and destination is the same. Then it does not do a transfer. Now, if it is based on the the source and destination not the same, then I have to look at the routing table, which actually is generated based on shortest hops. And then it goes off into the other systems. So here, if you notice, the other ones were all graphical. They showed you visually how things were going. You could see all the details. Here, we're doing it more of a text-based. So here, for example, I have the different signals, their periodicity, worst case execution time, and where their destinations were. And then you can see the list of tasks, what rate, how much time does it execute, what are the read-write buffers. It provides all of that information right here. And of course, here you can see what the routing tables were, like how is each one connected to each other in the particular system. So what we see over here is 3 things. If you recall, the task starts off here and the final termination is over here on T4. So what we're looking at is the latency that it takes to get from this point all the way to this point over here. You can see what the variation of latency, you can see a majority of it is right down here between 0.6 and 0.8, but you have one going all the way up to 0.8, probably 0.85. So 1.85 seconds. So the problem now is that you have a huge range. It's almost 3x the fastest time. So which means you have to take contingency to ensure that this data coming in so late in the process will not cause the rest of my system to slow down, causing other types of problems related to my autonomous driving. Now this one here, for example, shows me 2 of the sensors and shows me the activities as when they were all periodic. In this case, they are periodic, when they were triggered. There is also information as to when each the task completed, plus it gives you information about the utilization of every one of the ECUs. So for example, here I can see 199 of these tasks came in, 99 went out. There's like buffer occupancy of 2, and the maximum delay is about 200 milliseconds. So you have all of that information generated for you. You also have information on the devices, on the individual devices here. you can actually see, for example, the time activation, time finish, and time scheduler at the bottom shows you how long I was in the scheduler, and also shows me, at what time I was activated, and then, what is the response time or what was the processing time. So if you notice the last one, it did not actually have to wait. When it came in, it went out almost as soon as the task was completed. So there was no buffering for that particular task. But there can be other tasks that can cause things to get buffered. So allows me to be able to evaluate, even if I don't have all the details of the system, I just have limited data. Even at that point, allows me to evaluate what's the best distribution of these tasks. Now, let's take it one step further and look at it in even more detail. So now you know that your hardware platform is an ARM-based architecture. It's got an ARM Cortex-A77 with an external L2. It's got an AXI bus. It's got code links. It's got multiple systems, and then it's got it's got an Cortex in this particular case, but it's also got hardware accelerators. So now my goal is I've got this application software, which is a video rendering software. It starts from the sensor to the display on a HDMI. And what I want to be able to do is look at the power versus the amount of frames I can process and what's the cheapest way I can implement this. So, for example, here, what I have is I construct a model. Oops. I'm going to show you a variation of that model. I don't want the exact, but here we go. So in this particular case, what we have is we've got the CAN network, and one of the nodes of CAN is connected to a Drive PX, NVIDIA Drive PX chip. So that's the NVIDIA Drive PX chip. Multi-core ARM, if I go inside, it's got the 4 A72s, and it's got the 2 A72 Denvers as well, DMAs. So data coming in from the ARM, from the CAN bus, gets DMA to memory, gets triggered, does the processing, and then sends it out to the GPU to continue the processing. That's my sequence. So the white conversion, pre-processing, histogram, gives a decode, post-processing, and finally the rendering. So when I run this, you will notice that there's a completely different set of details that are generated here. The reason being that now you're no longer looking at just the the latency, but rather you're looking at, here's my power consumption. I'm looking at, for each piece of code, CUDA code that is executing on my graphic systems, what was the latency for each thread? And of course, here it shows me which signal or sensor was output. I can also look at, for example, the what was the memory used by each one of the processing engines within the within the Drive PX in the ECU. So it gives me now more hardware-related details. It gives me hardware-related information that I can then try to use. Is Drive PX really what I want to do, or do I want to use an NXP chip that has ARM and a GPU integrated into it? So, so those are things that you can evaluate very early in the design process. So it's after the stage which we saw earlier, which was this one over here. Oops, sorry. So this one over here, which was very abstract. I didn't have all the implementation level details, but here now, with this model, I've moved to something that's higher, an implementable. Because when I look at this model, it's got the exact configuration of my signals, my messages, the power information. Everything is located in this particular model. So it's not an abstract model, it's a very active model. And then when I go into these, I have all the details about the channels, the power consumption, the IND caches, has all of the information right here. Similarly with the GPUs, you've got number of threads, threads per warp. So these are all the standard parameters that go to define the GPU as well. So using this and using, say, the top level parameters, you can run more simulations, try out more configurations, and then see what the performance is going to look like. So for example, over here, what I have is I'm sending it out to a particular destination. But I could change this configuration where rather than sending it to a particular destination, I can say go find the destination. So for example, over here, this one uses a Renesas chip. And I have a database over here that tells me, like which function, which destination I want to go. I can actually change this configuration to say, hey, don't go to this chip, go to chip 2, or go to chip 6, or go to node 4. So I can modify that in the table here, and I can try different experiments to try to see what configuration is the best one to apply for this particular scenario or situation. As I mentioned earlier, if anybody has any questions, make sure to ask them on the chat window so we can answer them while we're going along. Or, of course, you can always wait till the end of the session and we can answer questions at that time too. Now, one of the things with autonomous driving is there's a lot of artificial intelligence, a lot of math-based algorithms. Now, one of the things that's very interesting in math-based algorithms is that you get to see a lot of analog experiments. So a lot of finding is that analog math-based implementation is actually fairly fast, plus it's also low power. So you can assemble models in Visual Sim where you can run these to look at, what happens if I use partially, some of it is done in analog, partially it's done close to the memory, some of it is done outside of the, it's more on the digital side. So then I can look at what is the correct, I can do two things. One is I can look at the correct, I can do three things. One is the correctness of the algorithms, are the waveforms working, generated correctly. I can then look at the power consumption, or power plot. And of course, I can also look at the timing latency. So single model, I've combined analog, digital, all the math operations, correctness of the algorithms, the power, and the timing of performance. Single model, combined all of them together. So this is an important consideration here where I'm no longer dependent on doing just the functional model or just the timing model or just the power, combines all of it into a single model. And you can do all of these starting where initially the function may be just a simple mode case. Mode 3 takes so many cycles. But rather later I can say, okay, mode 3, data coming in needs to be 400 bytes, and I'm going to do an FFT first. So you can have a variety of functions that can be run in your system. Now that you've seen how you can set up different types of partitioning, either across the network or within ECUs or a multi-core, let's also take a look at the aspects that are related to SOTIF and functional safety. SOTIF is the functional safety requirements for the more autonomous driving. So when you look at what functional safety is provided in Visual Sims, you can see it's really the overall safety of the entire system. So it's not just the power system or the braking system, but it's of the entire OEM, the whole vehicle. So you have to work on the software system and the semiconductors operating together in response to all the inputs. So Visual Sim, of course, provides the architecture exploration platform, and you can apply different failure cases, and then see what the responses are. Now, in the case of SOTIF, you're really depending on a lot of math algorithms, a lot of sensors like radars, lidars, cameras, proximity sensors, road condition sensors, a lot of those kind of things. And of course, there's actuators that run independent without having any human interference, right? So there are many scenarios that you might have. Some of them are, is it comprehending the data correctly? So if I find that the road was gravel, but does my application think it's asphalt? So then what happens? Also, the other one is that, for different temperature conditions or for different latencies across the network, how does my application respond? So here is a braking system as you can see, there's my network with a gateway, and you can see all the different sensors. I got the four wheels, the brake, the gyro, the ECU, all of them. And of course, here, what I have is, when I introduce the errors, you can see how the braking response keeps increasing. And also you can see what the actual speed was. Was it expected to be those speeds or a different speed? And here, which is where I'm going to move over to the model, is, so here's my network. I've got three independent CAN networks connected through a backbone gateway. And it's got all the different sensors. There's data coming in and the data going out. So the goal is when the brake pedal, or the proximity sensor, which is the autonomous driving part, triggers, it takes all the data that's available and at the brake ECU makes the decision as to how much of brake value should I apply. So when I go ahead and run the simulation, of course, you'll notice every model generates a variety of data. So for example, in this particular model, of course, we have the power consumption, which is something you've always seen. But in this case, if you start looking, we also can start generating information such as what speed the vehicle was running at and what was the latency for four different wheels. So you can see, from the time the brake request came in to the time that it actually applied. Now, if you look at this, this is really 200 microseconds versus 400 microseconds. But if you really look at it, it's double the time that it's taking for brake 1 versus brake 4. The other aspect, which is kind of important here, is that the system reads 2 and 3 correctly here, reads 2, 3, and 4 correct, but then it reads the wheel 1 incorrectly over here. It's incorrect data read. So it could be that the data is corrupted, or it could be that the data arrived too late, which means the data is not there, or it's an old data when it's trying to make a decision. The other aspect, which was like understanding the sensing input. So here, for example, the sensor said it was IC, but the algorithm took it as pavement. So rather than slowing down, you're actually speeding it up. So these are faults that can occur, and as a result of which you can have very disastrous situations. So not only are you doing a mapping, you're also looking at the functional safety aspect. Now what I'm going to do is I'm going to take this where I've got a multi-core architecture right over here. I'm going to open this. You can see I've got a multi-core A53 Cortex right over here. And what I'm going to do is I'm going to go ahead and create a scenario where a core fails, and I'm going to rerun the simulation to see what happens. Now, obviously, the thing that will really get impacted is this over here. The other ones we're not going to worry so much. Of course, you can see how much more the latency. So now you only have a single core to run, as opposed to earlier you had 2 cores to run, and you can start seeing how there's a more percentage of brake latency running at the higher level than at the lower level. So you can look at those aspects as well. Matter of fact, there's also another aspect here, which is you notice always these two are getting closer than those. It's also because the proximity between the brake ECU and the rear wheels versus the front wheels. So that's another aspect that's also because it's going across multiple gateways to get to the front wheels. So here, for example, I can also look at the hardware statistics of how much of data is flowing through the system, and what's my throughput. Shows me my my bridges and all of those aspects as well in the particular design. So what I can do is I can do a variety of trade-off studies here and also apply these different failures and see what happens, whether my system is working correctly or incorrectly. Now, we talked about a few failures in this particular case. One was, the sensing failure, which was a software not detecting it correctly. The other one was network failure, where we saw the latency was too high, so wheel one's data was not recognized in time. We also had where we lost a core, so we had a hardware failure. Now, you can also look at the power failure. Apologize, I think I closed the model. I'm going to go ahead and reopen the same model. Again, if you have any questions, feel free to type them on your control panel so we can answer the questions right away. So now what I'm going to do here is I'm going to add some power-related information into the model. And I just need to know what the power factor is. So here. So now what we're going to do is, in addition to looking at the latencies, looking at the correctness of the algorithms, looking at the sensors, we're also going to look at other aspects, which are, for example, the amount of what's the heat consumed, or what's the voltage curve in discharge and also in charging. So we're also going to look at other aspects of the system, not just the things. So for example, here you can see the range of joules that are being emitted by this particular design. Plus, you can see what your voltage curve was in this particular thing. So it's so you can actually study a variety of designs right over here. So, for example, in this particular thing, I have a complete database of a variety of batteries that I can select from, and I can set up other kinds of things like coefficients, temperatures, heat capacity, and a variety of other things also. Now, I can also do other things that I'm not going to do in this webinar, but we can also look at other aspects of the battery, which is battery life cycle, and also like impact of thermal shocks, impact of physical shocks, things like that as well. Now, this one here is a standard report that we generate. And in this particular case, you can see we just had a few things. This is just for the network failure. There's about 20 different items that are reported for network failure alone. But just to show you what it looks like, the output report, which is a CSV file, which is what the ISO 26262 requires to be able to put it into their system. And you saw this here. This one here just shows you a network failure model. So you have data coming, you have two flows, data coming in across the network and goes through. You establish a congestion at this particular network, and you can see what happens. So this is the failure with the resolution, failure without the resolution. So you can see it's a pretty flat latency, but here the latency range keeps going in a pretty huge, about almost 20% variation in the latency as opposed to being really flat. So allows you to be able to evaluate what exactly is your bottleneck, or what is the source of bottleneck which causes some system to fail. Now, one of the things to understand about failure is failure does not mean that the whole system just crashes. Failure means that the system may have certain problems, like, for example, some of the data does not arrive at the destination, or there's a temporary congestion or overload. Those are also considered failures in the design. Now, let's look at why this is preferred over the alternate techniques. So today, you can do these kind of analysis using analytical models, or get a real car and plug the software into the real car. The problem is spreadsheets and worst case execution time, highly inaccurate. You can use it as a good starting point, which is why Visual Sim uses those spreadsheets as inputs. But then the real system will not be available during the design, and each OEM is going to have a different configuration. So you cannot be building the prototype of a vehicle for all the different possible customers you're going to have. So it's really very difficult to be able to use a vehicle, real vehicle system. So what is Visual Sim proposing? It's like a library-based model. So every component you saw in those models of construction were taken straight out of a library, and then you integrate those with traces from existing system, as I said, spreadsheets, all of those. You construct the model, you generate the plots, the traces, your failure impacts, all of those, share it with the development team, and then you generate documentation that can then be sent off to the OEMs, tier one suppliers, semiconductor companies, all of those people. Now, one of the things that happens, in this case, I'm just taking a small subset, which is, I've got an IoT device inside the vehicle, and I need to be able to communicate with the V2V, but also to the data center. So, for example, this is the inside of my IoT system, has the sensor, the analog front end, MCU, in this case, we're using Bluetooth. So it goes out to a local hub, and then it heads out, it can either do local processing, which, might be like I'm accessing the street light, or I'm accessing a traffic signal or something in some other vehicle, or it can be sent out to the server and get a response back. And of course, each one of these has unique set of parameters, batteries, so you can evaluate power consumption, hardware, software configuration. Also, you can evaluate for different message sizes, what is my response time from the server to come back. So that is a significant part of my evaluation. Quick introduction to mirrorless design. We've been around for at least 15 years, lots of awards over time. We have built, or customers have built, over 250 different products using our libraries and our infrastructure. Now, mirrorless design, has provides software, which is the Visual Sim software, and a large library of components. So depending on what application you are, you get library models, templates, and a variety of other building blocks. Of course, we do provide training, plus we provide custom services, which includes, developing new libraries. Say you want a custom gateway, or you want a custom autonomous driving function, we can build those. Or we can build a complete model, say in a vehicle or a subsystem, to conduct parametric studies. Or you can give us a design and we can do architecture evaluation and provide you feedback. Now, quick introduction to Visual Sim Architect, which you've been seeing. One of the key things is you start graphically, but then you move to a command line. It's all library based, and you can incorporate a hardware, software, and network into the same model. Of course, you're looking at timing throughput. Power measurement is another aspect. And of course, the ability to incorporate the entire EE to semiconductor systems, so anything from your sensors, networks, hardware, software, semiconductors, everything can be incorporated into the same model. And you can do not just timing and power analysis, but also functional and safety analysis. The whole goal is to architect your full system. And as we just saw, we map different algorithms across multi-core or multi-distributed systems. One of the key things when we looked at this with the distributed design is trying to figure out what the resource requirements are, even while we're trying to bid on a project, or even while we're trying to sell this to potential car manufacturers. And of course, we talked about the safety standard, which is very testing to see if we are compliant. Now, why do people buy Visual Sim? As we saw, the alternates are just not efficient, but also the model construction time. It substantially is reduced over other approaches because they're library based, as a result of which you can do a lot of analysis up front, and a lot of the refinement can also be done before you start any implementation. So that way, you're eliminating a lot of your bugs and bottlenecks because you already identified those before you start your development. So you can reduce your development schedule, and we've seen anything from 25 to 30%. And of course, the average increase in revenue can be pretty critical if you can shave off, say, 6 months or 5 months off your development schedule. With this, I'd like to thank all of you for attending this webinar. And again, if you have any questions, feel free to ask them. But we're also available via email or any other approach to be able to give you feedback on mapping these autonomous driving algorithms. Now, also there is another webinar next week related, which is on functional safety and also on 5G. So, highly motivate you to attend those sessions as well.
This conference will now be recorded.